What's up everyone? New day, new lesson. Networking foundations, VPC, subnets, NAT, and endpoints. Short version. It's simpler than the docs make it look. Proof incoming. By the end of this video, you'll be able to look at any Amazon Web Services architecture and know which subnet a resource belongs in, how a private instance reaches the internet, and where the hidden networking costs hide. Here's the thing most people get wrong. Every single Amazon Web Services workload you've learned about in this course lives inside a network called a VPC, and the structure of that network decides what's exposed and what's protected. Get it wrong, and you either put a database on the public internet, or you quietly overpay every month. That distinction comes up regularly on the Cloud Practitioner exam, so let's build the mental model properly. Back in episode 3, we covered Amazon Web Services global infrastructure. A region is a geographically isolated location, and an availability zone is one or more data centers inside that region. Since then we've walked through EC2, RDS, S3, DynamoDB, and a whole catalog of services. Almost all of them are regional, and almost all of them launch into a network. Today we finally open up that network and see how it's wired. Before we get into the mechanics, let's pin down 5 terms you'll hear throughout this video. A VPC, or Virtual Private Cloud, is your own logically isolated network inside one region. A subnet is a slice of that network living in a single availability zone, and it's either public or private. An internet gateway is the component that connects a public subnet to the internet. A NAT gateway lets private instances reach out without being reachable themselves, and a VPC endpoint is a private doorway to Amazon Web Services that skips the public internet entirely. We'll take each of these one at a time. Networking is foundational because everything plugs into it, and there are 2 classic failure modes. The first is exposure. You accidentally leave a database reachable from the public internet, which is the kind of mistake that ends up in security headlines. The second is cost. Your traffic flows through the wrong component and you watch the bill climb for no reason. Both come down to understanding subnet roles, and that's exactly what we're going to fix. So what is a VPC? Really? It's a logically isolated virtual network that you define inside a single region. Think of it as your own private section of the Amazon Web Services cloud, walled off from everyone else's. It spans every availability zone in that region, so you can spread resources across data centers for resilience. And nearly every service you've learned about launches into a VPC. The one rule to hold on to: a VPC lives in exactly one region. If you want to operate in another region, you create another VPC there. Now, here's the single most important idea in this whole video. People assume a subnet is public because of some special setting, or because of where it sits. It's neither. A subnet is public for one reason only: its route table has a route to an internet gateway. If that route exists, the subnet is public. If it doesn't, the subnet is private. That's the entire definition. And once it clicks, the rest of networking gets a lot simpler. Here's the picture I want you to keep. Think of a VPC as an office building. On the left, the public subnet is the lobby. It has a front door to the street, which is your internet gateway. Visitors can walk in, so this is where your load balancer and your NAT live. On the right, the private subnet is the inner offices. There's no street door at all. Staff can still go out for lunch. That's outbound traffic, but a stranger off the street can't wander in. That's why your app servers and your database belong in the private side, tucked away from the front door. Don't take my word for it. Here's exactly how the Amazon Web Services documentation puts it. If a subnet's route table has a route to an internet gateway, it's a public subnet. If it doesn't, it's a private subnet. Notice there's nothing in there about settings or labels. It comes down entirely to that one route. When a scenario question describes a subnet, your first instinct should be to ask, does it have a route to an internet gateway or not? Let's take a quick breath and lock in what we have so far. A VPC is your isolated network inside one region. Subnets are slices of it, each living in a single availability zone. A subnet is public if it has a route to an internet gateway, and private if it doesn't. Now the natural next question is, how does each type of subnet actually reach the internet? That's where the two gateways come in. First, the Internet Gateway. You attach one per VPC, and Amazon Web Services builds it to be horizontally scaled, redundant, and highly available. You don't manage its capacity or worry about it failing. It gives resources in your public subnets bidirectional internet access, and that word bidirectional matters. Hosts out on the internet can initiate a connection inward to your resource, not just receive replies. That's exactly why only public-facing things, like a load balancer, belong behind it. One nice detail: the Internet Gateway itself is free. Here's the official wording, and I want you to focus on the second sentence. Resources in your public subnets can connect out to the internet, yes, but similarly, resources on the internet can initiate a connection inward. That two-way street is the defining feature of an internet gateway, and it's the reason you'd never want your database sitting directly behind one. Keep that bidirectional behavior in mind, because the next service is its mirror image. So what about the private subnet? Those inner offices still need to reach out sometimes, to download patches, call an external application programming interface, or API, fetch updates. That's the job of a NAT gateway. Picture a one-way mail room. The staff locked in the back offices can send letters out, and the replies come back to them. But no stranger off the street can mail themselves a way in. Connections only ever start from the inside. Outbound is allowed. Unsolicited inbound is blocked. And here's Amazon Web Services stating it directly. A NAT gateway lets instances in a private subnet connect to services outside your VPC, but external services can't initiate a connection back to those instances. That second half is the whole point. Your private instances get to reach the internet for what they need, while staying invisible to anyone trying to reach in. This is the answer to one of the most common networking questions you'll face. How does a private instance get to the internet? Let's put them side by side, because these two gateways are often confused. The Internet Gateway serves public subnets, it's bidirectional, the outside world can start connections inward, and there's one per VPC at no charge. The NAT Gateway serves private subnets, it's outbound only with replies allowed back, and no stranger can connect in. Here's a subtle one. In the traditional zonal mode, the NAT Gateway itself lives in a public subnet, though the newer regional mode we'll meet shortly drops that requirement. And unlike the Internet Gateway, the NAT Gateway is billed per hour plus per gigabyte of data processed. That billing detail comes back to bite people, and we'll come to it shortly. Let's trace the actual path. On the far left, an EC2 instance sits in a private subnet and runs a software update. Its request flows to the NAT Gateway, which is sitting over in the public subnet. From there, the traffic moves to the Internet Gateway, and finally out to the Internet. The reply travels back along the same path. The instance got what it needed, but notice the direction. Every connection started inside the VPC. No external host could ever start a session with that private instance. That's the safe pattern you'll reach for again and again. There's an older alternative you should recognize, called a NAT Instance, and questions often pit the two against each other. A NAT Instance is just an EC2 instance you set up to do this job, which means you patch it, you scale it, and you build your own failover. So by default it's a single point of failure. The NAT Gateway, on the other hand, is fully Amazon Web Services managed. No patching, it's redundant within its availability zone, and it scales bandwidth automatically. When a question asks how a private instance should reach the internet in production, prefer the managed NAT Gateway over the self-managed NAT Instance. That's Amazon Web Services' own recommendation. One caveat worth holding on to: a zonal NAT Gateway is redundant, but only within its own availability zone. It is not magically spread across zones. So traditionally, if you wanted true high availability, you deployed one NAT gateway in each availability zone and pointed each zone's private subnets at their local gateway. As of November 2025, Amazon Web Services also offers a regional NAT gateway mode that automatically expands across multiple zones in a region, giving you built-in multi-zone high availability without deploying one per zone. The zonal mode still exists and is the traditional behavior, so just know both options are on the table. The Q is the word redundant. A zonal gateway covers one zone, while regional mode covers the whole region for you. We're about halfway, so let's consolidate. The Internet Gateway gives public subnets bidirectional internet access. The NAT Gateway gives private subnets outbound only access, and it physically lives in a public subnet. For production, prefer the managed NAT Gateway over a self-managed NAT instance. So far, everything has been about one VPC talking to the internet. But what happens when you need two VPCs to talk to each other? That's the next piece. Here's the mental picture for connecting VPCs. VPC peering is like running a private phone line directly between two houses. That's great when it's just a couple of friends who want to talk, but to connect a whole neighborhood, you'd end up with a tangle of wires running between every pair of houses. A transit gateway is the telephone exchange sitting in the middle. Everyone plugs in once, and through that hub they can all reach each other. Hold that image while we look at each option. VPC peering is a one-to-one private connection between exactly two VPCs, and traffic between them stays on the Amazon Web Services network. But here's the property that trips people up. Peering is non-transitive. If VPC A peers with B, and A also peers with C, that does not let B and C talk to each other through A. Each pair needs its own direct connection. So as you add more VPCs, you need a full mesh of links, and the count grows fast. Peering is the right tool when you have a small number of VPCs. This is worth saying in Amazon Web Services' own words, because it's a classic point of confusion in real teams. VPC peering does not support transitive peering relationships. People genuinely expect traffic to hop from one VPC to another through a shared peered VPC in the middle, and it simply doesn't work that way. If you ever see a scenario where someone wants one VPC to act as a pass-through hub for others, that's your signal that peering is the wrong answer. Let me show you why this matters at scale, because the numbers are dramatic. If you wanted to fully connect 100 VPCs using peering, you'd need 4,950 separate peering connections. Every pair needs its own line, and that grows quadratically. Now look at the second bar. With a transit gateway, those same 100 VPCs need just 100 attachments, one per VPC, into the central hub. That gap is the entire argument for moving from peering to a transit gateway as you grow. So the transit gateway is a cloud router that connects many VPCs in a hub-and-spoke model. Unlike peering, its routing is transitive. Every attached network can reach every other through the hub. Each VPC attaches just once, instead of building separate links to all its neighbors. And it does more than connect VPCs to each other. It also centralizes your hybrid connectivity, so your on-premises networks coming in over a virtual private network, or VPN, or direct connect all land at the same hub. This is exactly the pattern a large enterprise would use when running networking centrally across dozens of accounts. Here's the decision rule in one slide. VPC peering is for connecting two VPCs. It's non-transitive. The mesh grows quadratically, so reach for it when you've got just a couple of VPCs. Transit gateway is for connecting many VPCs and on-premises networks. It's a transitive hub and spoke. Each VPC attaches once, so it's the answer at scale. The Q in a question is the count. 2 VPCs means peering, many VPCs means transit gateway. Now for a feature that's both a security win and a cost win: VPC endpoints. The idea is simple. When a private instance needs to talk to an Amazon Web Services service like S3, it doesn't have to go out through a NAT gateway and the public internet. A VPC endpoint gives it a private path that keeps the traffic entirely on the Amazon Web Services network. No internet gateway involved, no NAT device involved, and crucially, no NAT data processing charges. There are two flavors, and the difference between them is one of the most practical decisions you will make in VPC design. The first flavor is the gateway endpoint, and there are two facts you absolutely want to remember. First, it supports only two services, Amazon S3 and DynamoDB. That's it, nothing else. Second, it's completely free. It works by adding an entry to your route table, so traffic destined for S3 or DynamoDB takes the private path automatically, and because it's free, routing that S3 and DynamoDB traffic through a gateway endpoint instead of a NAT gateway eliminates the per gigabyte NAT fees you'd otherwise pay. S3 and DynamoDB only, and free, those two facts come up regularly. Amazon Web Services spells this out directly. Gateway VPC endpoints provide connectivity to Amazon S3 and DynamoDB without requiring an internet gateway or a NAT device, and there is no additional charge for using them. Both halves of that sentence are worth locking in: the two-service limit and the price. If you only remember one cost optimization fact about VPC endpoints, make it this one: S3 and DynamoDB get a free gateway endpoint. The second flavor is the interface endpoint, powered by Amazon Web Services private link. Instead of a route table entry, this one creates an elastic network interface with a private IP right inside your subnet, and your traffic flows through it. It covers most other Amazon Web Services, basically everything that isn't S3 or DynamoDB. Because it's a real network interface, it supports security groups, so you can control access at a fine grain. The trade-off: unlike the gateway endpoint, an interface endpoint is not free. It's billed per hour per availability zone, plus per gigabyte of data processed. Here's a cost decision practitioners run into constantly. Imagine a data pipeline pulling a terabyte of data a month out of S3, and that traffic flows through a NAT gateway. You're paying a per gigabyte data processing toll on every byte. For traffic a free S3 gateway endpoint would have carried at zero cost. It's like driving across town and paying a toll each way just to mail a letter to your next-door neighbor, when there's a free gate in the shared fence. The fix is one of the most common cost optimization moves there is: add S3 and DynamoDB gateway endpoints to your VPCs. Let's line up the two endpoint types. The gateway endpoint covers S3 and DynamoDB only. It's route table based, it's free, and it only serves the local VPC in the same region. The interface endpoint covers most other Amazon Web Services. It's an elastic network interface with a private IP. It's billed per hour plus per gigabyte, and it supports security groups. The quick mental shortcut: if the question mentions S3 or DynamoDB and cost, think free gateway endpoint. For anything else, it's an interface endpoint. Last piece of the puzzle: the default VPC. When Amazon Web Services creates your account, it hands you a ready-to-use VPC in every region, so you can launch something immediately without building a network first. It comes pre-built with a public subnet in each availability zone, an internet gateway already attached, and a route to that gateway. The default network ACL, which we covered back in episode 12, allows all inbound and outbound traffic, and the default security group allows all outbound traffic plus inbound traffic from resources in the same security group, but not from the open internet. And anything you launch into it gets a public IP automatically. Think of the default VPC as a furnished starter apartment where the front door comes already unlocked. It's wonderful for moving in fast. Everything's set up, you can drop a workload in and it just works. But you would not store your valuables in there without changing the locks first. That's the exact trade-off. Convenient to start with, risky if you treat it as a permanent home for sensitive workloads. A couple of things to keep in mind as we close this out. First, here's some good news that surprises people. If you delete your default VPC, you can recreate it yourself. Now, why might you want a fresh one? Because the default VPC's subnets are public and its default network ACL allows all traffic, it isn't production safe out of the box. Before you deploy anything sensitive, either harden it or build a custom VPC with proper private subnets, and recreating the default is easy. Since 2017, you just run Create Default VPC from the Amazon Web Services console or the command line interface, and Amazon Web Services rebuilds it for you, with no support case required. So deleting it isn't the dead end people often assume it is. Let's bring it all together with the pattern you'll see most often, the classic 3-tier web app, all inside one VPC. Up top, in the public subnets, sit the load balancer and the NAT gateway, the two things that legitimately need to face outward. Down below, in the private subnets, sit the app servers and the database, safely tucked away. Web traffic enters through the load balancer and flows down to the app servers. When those app servers need to fetch patches, they reach out through the NAT gateway, and the database never touches the internet directly at all. That separation, public for what faces out, private for everything else, is the whole game. Let's distill everything into the decision rules you can carry into any scenario. When a private instance needs the internet, the answer is a NAT gateway, managed and redundant within its as. Two VPCs talking means peering. Many VPCs or on-premises at scale means a transit gateway. For S3 or DynamoDB, use the free gateway endpoint. For most other services, use an interface endpoint. A subnet is public if it has a route to an internet gateway, and private if it doesn't, and always harden or replace the default VPC before production. Now let's see how well you absorbed all of this with a quick 5-question quiz. Alright, time to put your knowledge to the test. Question 1. An EC2 instance in a private subnet needs to download operating system patches from the internet, but it must not be reachable from the internet. What should you use? Is it A. Attach an internet gateway directly to the private subnet, B. A NAT gateway in a public subnet, C. A VPC peering connection to a public VPC, or D. A gateway endpoint for the patch repository? Run the decision rule from earlier before you answer. This one is B. A NAT gateway gives private subnet instances outbound-only internet access, and it sits in a public subnet. Attaching an internet gateway to the subnet would make it public and break the no inbound requirement, and gateway endpoints only serve S3 and DynamoDB, not a general patch repository. Question 2. A company needs to connect over 50 VPCs to each other and to its on-premises data center, with every network able to reach every other. Which option scales best? A. A transit gateway in a hub-and-spoke model. B. A full mesh of VPC peering connections. C. An internet gateway shared across all VPCs. Or D. An interface endpoint in each VPC. Think about which constraint matters most here. The right call here is A. Transit gateway is a transitive hub-and-spoke router where each VPC attaches just once, so it scales cleanly to dozens of VPCs plus on-premises. A full mesh of peering would need over 1,000 connections, and peering is non-transitive anyway, so it can't provide that any-to-any reachability. Question 3. A data pipeline reads large volumes of data from Amazon S3 and is currently routing that traffic through a NAT gateway, generating high data processing charges. What's the most cost-effective fix? A. Switch to an interface endpoint for S3. B. Move the pipeline into the default VPC. C. Replace the NAT gateway with a NAT instance. Or D. Add a gateway endpoint for S3. Lock in your answer before I give it away. If you said D, well done. A gateway endpoint for S3 is free and keeps the traffic on the Amazon Web Services network, removing those per gigabyte NAT charges entirely. An interface endpoint would work technically, but it's billed per hour and per gigabyte, so it's not the cost-optimal choice when a free gateway endpoint exists for S3. Question 4. What single factor determines whether a subnet is public or private? A. Whether the subnet's name contains the word public. B. Whether instances in it have private IP addresses. C. Whether its route table has a route to an internet gateway. Or D. Whether it spans multiple availability zones. Pause here if you want more time. It has to be C, and here's why. A subnet is public for exactly one reason. Its route table has a route to an internet gateway. The name is just a label. Every instance has a private IP regardless, and a subnet always lives in a single availability zone, never multiple. That one route is the whole distinction. Last one. Question 5. An architect peers VPC A with VPC B, and separately peers VPC A with VPC CC. They expect VPC B and VPC C to communicate through A, but it doesn't work. Why? A. VPC peering is non-transitive, so B and C cannot route through A. B. Peering connections expire after a set period. C. Each VPC can only have one peering connection. Or D. Peering only works between VPCs in the same subnet. Got your pick? Let's see. The answer is A. VPC peering is non-transitive, which means B and C can't talk to each other just because both are peered with A. You'd need a direct peering connection between B and C, or, once you're connecting many VPCs, a transit gateway to provide that any-to-any routing through a central hub. And that's networking foundations, VPC, subnets, NAT, and endpoints sorted. Every lesson in this series stacks, so the next one assumes today's ideas. Keep the streak going.